Assalamualaikum warahmatullahi wabarakatuh. Today our group will be presenting on the topic of external flow for DMID 1843 thermofluid. Before we begin our analysis, let me introduce myself and my teammates for this project. My name is Muhammad Adahmadi bin Muhammad Zulkifli, then Ahmad Nabil bin Asri Faris, next Muhammad Adib Arham bin Muhammad Nur Azwan, and lastly Muhammad Firas bin Suko Abdul Rahim. Now, let us move on to our introduction. Alright, for our assignment, we decide to choose the Mercedes-AMG F1 Team Car based on the new 2026 regulation concept. As we know, this car is manufactured by the Mercedes-AMG Petronas F1 team, and the estimate price for just one car over 15 million USD. If you look at the slide, the 2026 regulations actually make the car smaller and lighter. The maximum wheelbase is now 3.4 meters, the floor width is 1.9 meters, and the minimum weight of the car is around 768 kg. So, why did we choose this car? Because it's a perfect example of an external flow application. When the F1 car moves fast on the track, the surrounding air, which act as working fluid, flow directly over the outer parts of the car, like the front wing, the body, and the rear wing. Understanding this external flow is important because it helps the team control air resistance and creates downforce so the car can corner at crazy speed. That's all for the introduction part. I will pass to my teammates to explain about the mechanism.
Okay, let's move to the mechanism part. Firstly, we have the front wing, which is located at the front of the Formula 1 car. Its main function is to control the airflow as it first comes into contact with the car. The front wing generates downforce on the front wheels and directs air around and underneath the car. This helps improve grip, steering response, and overall cornering performance. Next, we have the rear wing, which is located at the back of the car. The rear wing generates downforce on the rear wheels, improving traction and stability during high-speed driving. It also helps maintain control when the car is cornering and work together with other aerodynamic components to optimize airflow. Next, we are going to the floor and venturi tunnels, which are located underneath the car. These components accelerate the airflow beneath the vehicle, creating a low pressure area under the floor. This low pressure generates a significant amount of downforce through the ground effect principle, helping the car stay firmly on the track and improving stability at high speeds. And lastly, we have the diffuser, which is located at the rear underside of the car. Its function is to expand and accelerate the airflow exiting from underneath the floor. This helps maintain the low pressure region under the car and increases downforce efficiently. As a result, the diffuser improves stability and cornering performance while minimizing aerodynamic drag. In conclusion, the front wing, rear wing, floor and venturi tunnels and diffuser are the main external flow mechanism in a Formula 1 car. These components work together to manage airflow, generate downforce, reduce drag, and improve the overall performance and stability of the vehicle during racing.
For this slide, Mach number is used to compare the speed of the Formula 1 car with the speed of sound. In this formula, M represents the Mach number, V is the velocity of the car in meters per second, and as A is the speed of the sound, which is approximately 343 meters per second. For example, if the Formula 1 car is traveling at 360 kilometers per hour, it is equivalent to 100 meters per second. Therefore, the Mach number is 100 divided by 343, which equals 0.29. Since the Mach number is less than 0.3, the airflow around the Formula 1 car is considered incompressible. This means the change in air density is very small and can be ignored during aerodynamic analysis. For Reynolds number, the Reynolds number is used to determine whether the airflow is laminar or turbulent. Since Formula 1 car travels at very high speeds, they have a very high Reynolds number. This means the airflow around the car is mainly turbulent, which is important for generating downforce and improving stability. For drag force, we can see that as the speed of the car increases, the drag force also increases significantly because the velocity is squared. Therefore, Formula 1 engineers designed the car to reduce drag while maintaining good aerodynamic performance. And lastly, for the downforce, this is used to calculate the downforce generated by the Formula One car. In this formula, Fl represents the downforce, V is the air density, V is the velocity of the car, Cl is the lift coefficient, and A is the reference area. The faster the Formula One car moves, the greater the downforce produced. Higher downforce increases tire grip, improves stability, and allows the car to corner at higher speeds.
Next, we talk about counter problem. First, we have porpoising, which is its ground effect instability. When the car is accelerates down a straight, the underfloor venturi tunnels generate a massive amount of downforce, pulling the car closer and closer to the track. However, when the car gets too low, the physical space underneath is restricted, causing the airflow to suddenly choke or stop. Because the downforce vanishes instantly, the car suspension snaps upward as the car rises. The airflow reestablishes, downforce returns, and the car is sucked up again. This creates a violent high-speed bouncing cycle that severely affects the driver vision and car stability. The second problem is aerodynamic drag and weak turbulence, famously known as a dirty air. As the Mercedes car cuts through the air at 350 km per hour, it's a complex wing and bodywork left behind a massive trail of highly turbulent, low-pressure air. If another car tries to follow closely behind, its aerodynamic surface the surface cannot function properly because the incoming air is no longer clean or laminar. This result is in severe loss of downforce for the trailing car, leading to overheating tire and making overtaking incredibly difficult. Finally, a major fluid mechanic issue of boundary layer separation and aerodynamic stall. This happens when airflow travel over aggressively curved surface such as a steep rear wing, angle or tight side port taper. As the air moves along the surface, it encounters an adverse pressure gradient, meaning it is forced to move from low pressure to high pressure. Then the thin boundary layer closer to the car body lose its kinetic energy, slow down and completely detaches or separated from the surface.
Despite this F1 team doing so good this season, it has its own problems. For instance, high aerodynamic sensitivity that can cause performance losses when following another car closely behind due to turbulent airflow, which is also can be called dirty air. Not just that, the external factors such as strong crosswinds, tire degradation, and cooling issues can be also affect the car's overall performance. Aerodynamic development. This is for improvement. Continuously computational fluid dynamics (CFD) can be used, which is a computer-based system to help engineers to know about their car more. Why CFD is important? CFD is to reduce drags by using mathematical order. It reduces drags by the calculation and also the data tracked by the simulation. But it has lots of limitations, such as the result may not be perfect because of the mathematical order and not using the real-world experience, and also wind tunnel testing. It requires high power and cost, but it is way more cheaper than high wind tunnels. Still needs wind tunnel and track testing for validation. Next, wings and bodywork. The front wing, rear wing, and also bodywork can be optimized to improve external airflow around the car. This is when the car is going at the straight with higher speeds. The drag is too much when the external airflow is not controlled because of the aerodynamic is not streamlined. A streamlined design helps reduce drag, minimize turbulence, and maintaining sufficient downforce, and also helps the car get to a higher speed and also maintaining the stability in straights and cornering in very high speeds. In conclusion, this assignment demonstrates the application of external flow principle through the Mercedes-AMG F1 team car with the 2026 regulations. The airflow around the vehicle plays an important role in determining the drags, the downforce, stability, and overall performance of the car. By applying fluid mechanics concepts such as Reynolds numbers, friction effects, and aerodynamic principle, the car able to achieve the high efficiency at extreme speed during corners and straights. The study also highlights several challenges and possible improvements that can further optimize airflow and enhance racing performance. Overall, the understanding external flow is essential in designing the parts, the bodyworks, and the development of the car itself of modern Formula One vehicle is very important.
This is the example of CFD, computational fluid dynamics. In F1, this is a computer-based simulation method used to study how airflow flows around the car. It allows engineers to predict aerodynamic performance without building physical prototypes. Why CFD is important? Because it helps reduce drag to increase top speeds, generates downforce to improve cornering grips, and also save time and cost compared to repeatedly testing parts in wind tunnel. If you asked how CFD works by engineers create a detailed 3D model of the car, specialized software dividing the surrounding air into millions of small cells. Advantages. It has a lot of advantages, such as faster development process, lower cost than physical testing, ability to test many design variations. But it has its limitations, such as simulations must be still validated using wind tunnel testing and real track data. Thank you, that's all from us.